Steyr, Austria, 1967. The conference room at Steyr Daimler-Puch's small arms division held 7 engineers and one question that nobody wanted to answer honestly. What happens when a neutral country needs to modernize its entire military rifle inventory with exactly 0 colonial legacy, 0 testing infrastructure, and 0 tolerance for procurement failure? Horst Wesp sat at the far end of the table, 29 years old, recently promoted to lead designer for military hardware development. In front of him lay sketches that would have been dismissed as science fiction in most circles. A rifle with the magazine behind the trigger, a transparent ammunition window, a receiver made primarily of plastic. Not prototype ideas, production proposals. The Austrian military's requirements document sat open between them, effective range 300 meters minimum, weight under 3.5 kilograms, length suitable for both mechanized infantry and alpine troops. Reliability, function in temperatures from 40 degrees C to plus 150 degrees C. Modularity, adaptable to multiple tactical roles without requiring entirely separate systems. And the constraint that shaped everything else. Cost per unit could not exceed what Austria currently paid for antiquated post-conflict rifles that were becoming embarrassingly obsolete. Wesp's supervisor, Karl Wagner, kept returning to one line in the specification: universal applicability across all infantry branches. In traditional thinking, this meant compromise, a rifle adequate for everyone, optimal for no one. But Wesp saw it differently. He saw an engineering mandate to solve the actual problem rather than replicating historical solutions that no longer matched contemporary constraints. Polymer receiver, Wesp said, tapping the sketch, not furniture, structure. The room went quiet. In 1967, polymers meant consumer products, not defense equipment. Major global conflicts were being fought with aluminum and steel. The Soviet Union was fielding stamped sheet metal. Nobody, absolutely nobody, was proposing to build the central load-bearing component of a military rifle from plastic. The material science exists, Wesp continued, polyamide reinforced with glass fiber. We can achieve yield strength comparable to aluminum at 40% of the weight. More importantly, we can mold complex geometries that are impossible with traditional machining. The trigger housing, magazine well, and carrying handle become a single integrated unit. No separate components to align, no hand-fitting required, no tolerance stacking. He pulled out a second sketch showing the bolt carrier group. Gas-operated rotating bolt. 7 lugs engaging a steel insert in the polymer receiver. The insert carries all the locking stress. The polymer provides structural integration. Short-stroke piston system, self-regulating across different barrel lengths. We design the gas port geometry to maintain consistent cycling pressure, whether we're using a 350mm barrel or a 621mm barrel. Wagner leaned forward. Barrel lengths plural. Explain. Quick change system, Wesp said. 1 receiver, multiple barrels. A user can convert from close quarters configuration to standard infantry rifle to light support weapon by swapping barrels. No tools required. 60-second procedure. The engineering team exchanged glances. The Austrian military had watched international logistics multiply into nightmare complexity. Separate supply chains for carbines, rifles, and support weapons. Wesp was proposing to collapse all of it into modular configurations of a single base platform. The barrel release mechanism uses a simple lever lock, he continued. Spring-loaded detent holds the barrel assembly to the receiver. Depress the lever, rotate 90 degrees, the barrel separates. Reverse the procedure to install a different length. The gas system compensates automatically, no adjustments needed. One of the senior engineers raised the obvious objection. Bullpup configuration means the action sits next to the user's face. Any catastrophic failure vents forward through the magazine well and downward through ejection ports designed with blowout geometry, Wesp interrupted. We engineer for failure modes. The polymer receiver can be designed with stress relief channels that direct overpressure away from the user. This isn't theoretical. We calculate the failure pathways during the design phase. He showed them the final sketch, the complete rifle. Barely 790 millimeters long, with a 508 millimeter barrel, delivering full-length ballistics in a package shorter than most submachine guns. The bullpup architecture wasn't aesthetic. It was pure geometry serving tactical requirement. If stories like this help you see how engineering quietly shaped history, tell us in the comments what surprised you so far, and stay with us for the next chapter. The Austrian Ministry of Defense responded to Steyr's initial proposal with skepticism wrapped in bureaucratic politeness. They wanted proof of concept. They wanted metallurgical testing. They wanted field trials that wouldn't embarrass Austria if the polymer receiver failed during intense use. Most of all, they wanted assurance that a 30-year-old designer without field experience wasn't leading them into procurement catastrophe. Wesp spent 1968 and 1969 building prototypes in near isolation. The polymer receiver presented manufacturing challenges that had no historical precedent in this industry. Traditional injection molding couldn't achieve the dimensional tolerances required. The receiver needed to maintain alignment between barrel extension, bolt carrier rails, and trigger mechanism to within hundredths of a millimeter. Standard polymer molding techniques delivered accuracy measured in tenths of millimeters. He worked with chemical engineers at BASF in Germany, testing polyamide formulations. Pure PA66 offered excellent tensile strength, but poor dimensional stability across temperature extremes. Adding 30% glass fiber reinforcement improved rigidity, but made the material brittle under impact. The solution came from hybrid formulation. Shorter glass fibers for impact resistance, longer fibers for structural rigidity, precisely controlled fiber orientation during the molding process to align strength along stress vectors. The bolt design consumed 6 months of iteration. 7 lugs instead of the more common 6 or 8, an odd choice that raised questions during every technical review. Wesp's reasoning was purely mathematical. 7 lugs distributed locking stress more evenly than 6, provided better resistance to bolt setback than 8, which created thinner, weaker lug geometry, and allowed a shorter bolt rotation angle of approximately 22.5 degrees compared to the 60-degree rotation required by 3-lug designs. Faster unlock cycle, less carrier travel needed, shorter receiver possible. Gas system tuning proved even more demanding. Wesp needed one gas port geometry that would reliably cycle the mechanism across 4 different barrel lengths, 350 mm, 407 mm, 508 mm, and 621 mm, without adjustment. Too much gas pressure with the short barrel would batter the bolt carrier and accelerate wear. Too little with the long barrel would cause failure to cycle. The solution required calculating pressure curves for each barrel length, modeling gas expansion rates, and engineering a port diameter and piston face area that fell within the functional window across all configurations. By 1970, Wesp had functional prototypes. They worked, they cycled reliably, they maintained accuracy, but they looked alien. The transparent polymer magazine particularly drew criticism. Procurement officers saw it as a gimmick, a cosmetic feature that compromised tactical effectiveness by potentially reflecting light and revealing a position. Wesp's counter-argument was information theory. A user's decision cycle, observe, orient, decide, act, depended on information quality. Ammunition remaining was critical tactical information. Traditional rifles required either counting rounds, unreliable under stress, checking weight, imprecise, or visually inspecting the magazine by removing it. Time-consuming, breaks the firing position. The transparent magazine provided instant, accurate ammunition state without any additional action required. The tactical advantage of eliminating uncertainty outweighed the negligible visibility concern. especially since the magazine sat inside the grip, largely shielded from external observation. The Austrian army scheduled evaluation trials for 1971. Wesp's prototypes would compete against the Heckler & Koch HK-33, the SIG GSG 540, and the Beretta AR-70, all conventional designs from established manufacturers with proven track records. The test protocol was deliberately punishing. Accuracy trials, endurance firing, environmental exposure, rough handling, parts interchangeability, maintenance requirements, and cost analysis. Steyr arrived with 3 complete units and enough modular components to configure 12 different variants. Wesp insisted on demonstrating the quick-change barrel system first, not as a party trick, but as fundamental capability. In 45 seconds, he converted a compact 350mm configuration into a 621mm precision setup, then back, then to 580mm standard, then to 407mm. Each configuration achieved first-round hits at appropriate ranges without adjustment, because the optical sight was integrated into the carrying handle, not mounted on the barrel. The evaluators watched in silence. This wasn't modularity in the theoretical sense. It was operational flexibility that could actually be executed under field conditions. A single individual could carry 2 barrels and adapt to mission requirements that traditionally would have required completely different equipment. The mechanism Wesp presented to the evaluation committee was deceptively simple in concept, brutally complex in execution. At its core, the AUG functioned on principles established decades earlier: gas-operated rotating bolt, spring return. But the integration achieved something fundamentally different from its predecessors. When a round was fired, expanding gases drove the projectile down the barrel while simultaneously diverting a small portion through the gas port. This high-pressure gas entered a cylinder containing the piston, not a long-stroke system like the AK-47, where the piston traveled the full length of movement, but a short-stroke design where the piston moved approximately 5 millimeters before transferring kinetic energy to the bolt carrier and stopping. The genius was in the self-regulation. Wesp calculated the gas port diameter and piston face area so that across all 4 barrel lengths, the impulse delivered to the bolt carrier remained within functional parameters. With the 350mm barrel, the port sat closer to the chamber where pressure was higher, but the shorter barrel meant less total propellant burned, resulting in a specific pressure curve. With the 621mm barrel, the port sat farther from the chamber, where pressure was lower, but more complete propellant combustion provided different gas characteristics. The geometry he engineered created overlap in the functional windows. The bolt carrier, once impulsed rearward, traveled approximately 8 millimeters before cam surfaces engaged the bolt lugs. This rearward movement prepared the internal hammer through a connector that bridged the forward-mounted action to the rear-mounted trigger group. The cam surfaces then rotated the bolt 22.5 degrees, disengaging the 7 lugs from the barrel extension. Here was where the polymer receiver showed its value. In a traditional metal receiver, the bolt carrier rails had to be machined with precise parallelism and surface finish. Any deviation caused binding, wear, or accuracy problems. Wesp's polymer receiver molded the rails as integral features with the exact geometry needed. No secondary machining required. The steel wear surfaces where the bolt carrier actually contacted the receiver were molded in inserts, positioned with precision that hand assembly couldn't match. Extraction occurred during bolt rotation. The extractor claw held the spent case rim while the bolt rotated, breaking the case free from the chamber walls. As the carrier continued rearward, the ejector kicked the case out through the ejection port. The design was ambidextrous by component swap. A right-handed user had the ejection port on the right side, but by rotating the bolt 180 degrees and installing a blanking plate on the opposite side, the same receiver became left-handed configured. The recoil spring, housed in the buttstock directly in line with the bore, drove the bolt carrier forward. The carrier stripped a new round from the magazine, chambered it, and the cam surfaces rotated the bolt back into battery, locking the 7 lugs into engagement. The entire cycle, from ignition to ready to fire again, took approximately 80 milliseconds at a rate of 680 rounds per minute. But the real engineering achievement was in the modularity that didn't compromise the system. Each barrel was a complete assembly. Barrel, gas block, front sight and suppressor, all precisely test-fired as a unit. When a user swapped barrels, they weren't just changing tube length, they were installing an entirely pre-calibrated subsystem. The receiver remained the constant, the barrels became variables. The trigger mechanism lived in a separate housing that could be removed as a complete unit by pushing 2 pins. This meant trigger work could be replaced or repaired without disassembling the entire unit. More critically, it meant quality control during manufacturing could test and validate trigger groups independently, then install them into receivers as matched assemblies. The optical sight integrated into the carrying handle wasn't an afterthought. It was structural architecture. The handle formed a bridge over the receiver, providing a rigid mounting point that couldn't lose its alignment because it wasn't attached to the barrel. The 1.5x magnification was calculated as an optimal compromise. Enough magnification to identify targets at 300 meters, wide enough field of view for close awareness, and simple enough to manufacture affordably. Wesp had engineered a system where every major component could be separated, inspected, replaced, and reassembled without specialized tools. The design philosophy wasn't just modularity, it was maintainability by deliberate architectural choice. Do you think this design choice was inevitable or a risky gamble at the time? Share your view in the comments and pass this story to someone who enjoys understanding how things really work. The 1971 trials exposed the AUG's vulnerabilities with precise brutality. Austrian army testers subjected the prototypes to environmental conditions that went beyond specification requirements. Immersion in water followed by freezing, burial in sand followed by use without cleaning, repeated drops onto concrete from shoulder height while loaded. The third prototype's receiver cracked during the drop test, not a catastrophic failure but a hairline fracture along the ejection port that grew during subsequent use. Wesp retrieved the damaged unit and spent 3 days studying the failure under magnification. The crack originated at a stress concentration point where the polymer thickness transitioned abruptly near the port opening. His initial design had assumed uniform stress distribution. Reality demonstrated that impact loading created localized stress spikes. He returned to the polymer formulation engineers with specific requirements: maintain the 30% glass fiber content, but modify the fiber length distribution to include a percentage of ultra-short fibers specifically for crack resistance. More critically, he redesigned the ejection port geometry, adding a gradual thickness transition and subtle radius to eliminate the sharp corner that had acted as a crack initiator. Image showing stress concentration points on a polymer structure during impact. The cold weather testing revealed another issue. At 30 degrees CC, the recoil spring's properties changed enough to marginally reduce reliability with certain ammunition lots. Not a failure exactly, but inconsistent performance that would be unacceptable in the field. Wesp couldn't change spring metallurgy without extensive retesting, so he approached the problem from a gas system perspective. He opened the gas port by 0.3 millimeters, enough to increase the impulse delivered to the bolt carrier in cold conditions, but not enough to cause overpressure problems at normal temperatures. The margin was thin, but testing confirmed it worked. The accuracy trials produced unexpected results. The AUG consistently delivered 2.5 MOA groups at 100 meters, acceptable for a service rifle, but not exceptional. A competing design, the HK-33, was achieving 1.5 MOA. The evaluation committee noted this in their report as a potential deficiency. Wesp's response challenged their metrics. He set up a demonstration using 6 units, 3 AUGs and 3 HK-33s, all randomly selected from production batches. He asked each tester to use each weapon without any individual adjustment. The AUGs maintained 3 MOA across different users. The HK-33s varied from 1.5 to 4 MOA, depending on how the individual unit's sights happened to be adjusted for that particular user. His point was architectural. The conventional design required individual zeroing because its sights mounted to the barrel, and manufacturing tolerances meant each unit needed personalized adjustment. The AUG's sight was integrated into the receiver, factory calibrated during production. Any AUG could be picked up by any user and achieve effective hits without adjustment. In operational context, this reliability across users outweighed marginal precision advantages that required individual customization. The endurance trial was pure attrition. 10,000 rounds per unit without cleaning, only adding lubrication as needed. The AUG's gas system began showing carbon buildup around the piston cylinder by round 6,000, causing occasional cycling issues. Wesp had anticipated this and designed the system with enough gas port margin to compensate, but it became clear that field maintenance would require more frequent piston cleaning than traditional systems. He redesigned the piston cylinder with a slightly larger diameter and added shallow spiral grooves to the piston face. The grooves allowed carbon particles to be pushed forward during cycling rather than accumulating in the cylinder. Combined with a harder chrome lining in the cylinder bore, the modification extended reliable cycling to beyond 12,000 rounds in retesting. By late 1972, the Austrian Army's evaluation committee had enough data. The AUG wasn't the most accurate rifle. It wasn't the lightest, it wasn't the cheapest per unit, but when evaluated as a complete system, reliability, modularity, maintainability, training time reduction, and logistics simplification, it solved more problems than any competing design. The polymer receiver that had seemed like reckless innovation proved to be the element that enabled everything else. The revelation came not during design or testing, but during the Austrian Army's maintenance training program in 1974. Wesp was observing recruits being taught weapon disassembly, standard procedure for any newly adopted rifle. The instructor began by laying out tools, punches for driving pins, screwdrivers, cleaning rods, and brushes. Wesp interrupted. "No tools needed." The instructor looked skeptical. Every service rifle he'd trained on for 20 years required at least basic tools for field stripping. He asked for a demonstration. Wesp took an AUG from the rack. He pressed the barrel release lever and rotated the barrel assembly 90 degrees. It separated from the receiver. No punch, no hammer, just finger pressure and rotation. He pushed 2 captive pins at the rear of the receiver. The buttstock separated, revealing the recoil spring assembly that could be lifted out. He pushed 2 more pins securing the trigger housing. The entire trigger mechanism dropped out as a self-contained unit, 45 seconds from a complete rifle to 6 major assemblies, each of which could be inspected, cleaned, or replaced independently. Reassembly took slightly longer, 60 seconds, because alignment mattered, but still required nothing except human hands. This was the final curiosity that explained everything. Wesp hadn't designed a modular rifle. He'd designed a rifle built entirely from modules, each of which could live independently. The barrel wasn't attached to the rifle. It was a subsystem that connected to the receiver. The trigger wasn't built into the frame. It was a component that installed into the receiver. The stock wasn't furniture, it was a housing for the recoil system that also provided a shoulder interface. The implications cascaded through military logistics. Armorer training time dropped by 60% because there was no complicated disassembly procedure to memorize. Every major component had an obvious release mechanism designed to be manipulated without tools. Parts inventory could be organized by module rather than by individual components. Instead of stocking 50 different small parts, armories stocked barrel assemblies, trigger housings, bolt carriers, and receiver units. Field repairs transformed from specialized work to user-level tasks. A damaged barrel didn't require a trip to the armory, it required a replacement barrel assembly that any user could install in under a minute. A malfunctioning trigger didn't mean the entire rifle was out of service, it meant swapping the trigger housing. Even the bolt could be extracted by depressing a release and pulling rearward, no tools, no special procedures. Wesp's design choice went further. Each module was designed to fail gracefully or be bypassed if damaged. The optical sight could be removed, exposing backup sights molded into the receiver. The standard barrel could be replaced with a heavy barrel for sustained use. The trigger housing could be swapped for versions with different characteristics. The rifle wasn't just modular in theory. It was architected so that every tactical scenario had a module swap solution. Procurement officers began understanding what Wesp had engineered. The AUG wasn't competing against other rifles. It was competing against entire portfolios. A traditional force used different equipment for different roles. Compact units for vehicle crews, rifles for infantry, precision units for designated marksmen, and light support units. Each required separate training, maintenance, and logistics. The AUG collapsed all of it into configurations of a single platform. Same receiver, same bolt, same trigger, same basic manual of operation. Only the barrel changed. A user trained on one AUG configuration could operate any AUG configuration. An armorer maintaining one version could maintain all versions. A logistics chain supplying one type of rifle could supply all tactical variants. This was why the transparent magazine mattered, why the polymer receiver mattered, why the quick-change barrel mattered. None of these features existed for their own sake. They existed because Wesp had conceived the rifle not as a tool, but as an engineered system where every component served the goal of operational flexibility through modularity without tools. By 1977, when the AUG entered full production, Steyr had delivered something genuinely unprecedented, a service rifle where changing mission requirements didn't require changing rifles. The hardware adapted, the user remained constant, and the logistics that had historically consumed 40% of small arms expenditure simplified into managing modules instead of managing specialized equipment. The Steyr AUG entered service with the Austrian Army in 1978 under the designation STG-77. Within 18 months, it was being evaluated by forces across 3 continents. By 1985, it equipped defense forces in Australia, New Zealand, Ireland, Saudi Arabia, Malaysia, and Argentina. By 1990, over 20 nations had adopted it in some capacity. By 2025, nearly half a century after Wesp's initial design, modernized variants remained in frontline service worldwide. The design's longevity came from architectural decisions that transcended 1970s technology. When optical technology advanced, the AUG adapted by adding Picatinny rail systems to the carrying handle. The modular philosophy extended to accept new sighting solutions. When specialized equipment became common, the quick-change barrel system allowed dedicated configurations without modifying the core rifle. When different calibers became tactically relevant, the modular receiver architecture enabled 9mm conversions for specialized units. But the AUG's true legacy wasn't adoption statistics. It was a philosophical shift in how engineers approached design. Before the AUG, modularity meant interchangeable parts that could be swapped during manufacturing. After the AUG, modularity meant interchangeable subsystems that could be reconfigured in the field by users. The distinction fundamentally altered what an infantry tool could be. Wesp's polymer receiver precedent opened material science exploration across the industry. By the 1990s, major manufacturers were incorporating advanced polymers not as cosmetic furniture, but as structural components. The weight savings, corrosion resistance, and manufacturing precision that Wesp achieved in 1970 became baseline expectations. The skepticism that had greeted his initial prototypes had transformed into an industry standard. The bullpup configuration itself remained a point of debate. Many forces rejected it on ergonomic grounds, and the AUG didn't change that. But the AUG proved that bullpup architecture could deliver reliable, accurate, and maintainable service rifles when engineered properly. It provided proof that unconventional configurations could meet strict requirements without compromise. Perhaps most significantly, the AUG demonstrated that intelligent modularity could solve procurement complexity. Global forces had struggled with the tension between specialized equipment for specific roles and logistical sustainability. The AUG showed that this wasn't an inevitable trade-off, that thoughtful engineering could deliver role-specific capability through configuration rather than through separate systems. Horst Wesp continued working at Steyr into the 1990s, leading refinements and updates to his original design. The AUG A2 added improved rail systems. The AUG A3 integrated modern mounting standards. Each evolution maintained the core principle: modules that could be understood, maintained and reconfigured by users rather than requiring specialized technical knowledge. When Wesp retired, the rifle he'd designed in his early 30s was serving its third generation. His polymer receiver, once considered dangerously experimental, had proven more durable than many metal alternatives. His quick-change barrel system, once questioned as unnecessary complexity, had become the feature that justified the AUG's continued relevance as mission requirements evolved. The engineering lesson wasn't about specific technical choices. It was about solving actual problems rather than replicating familiar solutions. Wesp looked at a universal rifle, not as one that compromised to serve all roles adequately, but as an architecture that could be configured to serve each role optimally. The distinction mattered. In 2025, updated AUG variants equipped specialized units, conventional infantry, and law enforcement across dozens of nations. The fundamental design, polymer receiver, rotating bolt, short-stroke gas piston, and quick-change barrel, remained essentially unchanged from 1977, not because innovation stopped, but because Wesp had engineered something that didn't need to be replaced, only adapted. The Steyr AUG proved that truly modular architecture doesn't age, it evolves. The rifle lying on Wesp's workbench in 1967 solved 1977's problems, but the architectural philosophy he embedded in that design continues solving problems that hadn't emerged yet when he drew the first sketches. That's the legacy of engineering that prioritizes systemic flexibility over optimized rigidity. The system works because every component was designed to work with any other compatible component. The design endures because that principle doesn't expire. If you enjoy calm, true stories about how engineering shaped the world, subscribe to the channel, leave a like, and tell us from which country you're watching.